The next section out of the sets unit is on subsets. What we're going to do in this section is define what both a subset is and a proper subset, and work some practical examples that compare sets using the subset notation. First thing we want to do is define what a subset is. So a set B is a subset of C if every element in B is an element of C. The way we write that symbolically is B is a subset of C. Here is an example of a subset. So notice the question says, is A a subset of C? Well, if we compare the two sets, this is A, is 1, 2, 3, 4, 5, and C is 1, 2, 3, 4, 5, 6, 7. Then what we're doing is comparing the two. Answering the question is basically, is A a subset of C? And what we can do is actually what they kind of refer to as chasing elements. So if we look at all the elements of A, let's see if they're contained in C. And if we do that, if we go through it, 1's in C, 2's in C, 3 is in C, 4 is in C, and 5 is in C. So therefore, every element in A is contained in C. So we can refer to as A as being a subset of C. By the way, a set can be a regular subset of itself. So, for example, 1, 2, 3 would be a subset of 1, 2, 3. I'll touch on that in a little bit later. Let's go ahead and define what a proper subset is. Now, a set B is a proper subset of C if every element in B is an element of C, and the set C has at least one element that does not lie in B. Now, we write this symbolically a little different. We write it as B, and there's no bar under the sideways U-looking symbol. So B is a proper subset of C. Going back to those exact same sets, where A is 2, 3, 4, 5, and C is 1, 2, 3, 4, 5, 6, 7. We have really two stipulations here. If I go back to the old definition again, it's the definition of a subset. Everything in B has, every element of B has to be an element of C. But you have an extra property, which is that the set C has at least one element that does not lie in B. So when we do this chasing of the elements, again, as you can see, 1's there, 2's there, 3's there, 4's there, 5's there. But we also have extra elements in the second set that are on the first, so we're good. There are actually elements in C, 6 and 7, that are in A, that are not in A, excuse me, not in A. And you only have to have one element extra. I mentioned two, but the only requirement is to have one element that's not in the first set. So if it were, say, C were 1, 2, 3, 4, 5, 6, it would still work the same way. One way to kind of make the difference between these two, this is subset. You know, the U, sideways U with the bar, and then subway is subset is just the sideways U without the bar. Much like when you're in algebra, this is x is strictly less than 2. The bar, if I have it there, this will be x is less than or equal to 2, which means it includes 2 as well as all numbers less than 2. So that bar symbolizes inclusion, which means in this case, with a subset, it can be the set itself. Okay, so I may not work all the examples on this PowerPoint. It's kind of a lot of overlap. But in any event, let me go ahead and go through this example 1 of my slides. And often in the examples in the next 2 notes that are on sets, often the examples I will give you select sets, like A is 1, 2, 3, 4, 5, 6, B is 1, 3, 5, C is 2, 4, 6, D is 1, 3, 5, 7, and E is 1, 3, 5. And I will ask you to, perform certain operations with those sets. In this case, we're looking at subsets. So the first question is A a subset of C? B is 1, 3, 5. I'm just going to go ahead and write these down. C is 2, 4, 6. And that way I can kind of point to these sets. I don't know how well that green will show up, so I'll write it in black. All right, so part A says, is A subset of C? Well, let's trace elements. So is A, which is 1, 2, 3, 4, 5, 6, a subset of 2, 4, 6. And right away you're going to see we have a problem. And that is when you try to trace 1, 3, and 5, they are not in C. So obviously the answer is no. Because not all the elements of A are in C. We just pointed that out. Okay, is C a proper subset of A? So remember, if it's proper subset, it can't be the set itself, and you have to have extra elements in A that are not in C. So if we trace, 2 is in A, 4 is in A, 6 is in A, we have extra elements in A that are not in C, so it looks like our definition works. So again, everything that lies in C does lie in A, and there are elements in A that are not in C. Okay, is B a subset of A? And again, chasing elements, 1's there, 3's there, 5's there, so we're good. So we got containment. Everything in B is in A. Is B a subset of E? Well, if we trace 1, 3, well, wait a minute, I got to write down. I was thinking it was A, my mistake. Let's write down E, which is 1, 3, 5. And if you notice, those two sets are actually equal. But with the regular subset definition, that works. Because that's all you need is containment. And 1's in there, 3's in there, 5's in there. Now, if you do part E, that's one that you need to have the extra property. So we just showed containment. But the problem is, E does not have an element that's not in C. We need an extra element in this set that's not in B. So, forgot to write the answer down. We showed that was true, and we just talked about this because these sets are equal. They cannot be proper subsets. So the proper subset can never be the set itself. Now, with a regular subset, where you have the bar, it can be the set. The two sets can actually be equal. and be subsets. And again, that kind of goes, I'll kind of go back to that idea of like in algebra, the difference between these two statements is this answer actually does contain the number 3. This is just strictly less than 3. So that bar signifies, in a sense, equality. In this case, equality with sets is the same number of elements, or the same sets, literally. All right, I'm going to leave this example for you to work on your own. The answers are there. Same here. What I'd like to do, because I want to make these videos relatively short, doing them the first time around, just to kind of hit the main points and show, get that where I'm actually maybe going into more detail and maybe demonstrating a few things that you might be able to get out of it as opposed to just reading my notes or reading the book. But I'm going to try to highlight the main points. The last thing in this section is to take a given set and list all the subsets of that set. So what I'm going to do is take, as you can see, example 4 is list all the possible subsets of 1, 2. Now, let's think about this. What sets could be represented that are subsets of 1 and 2? Well, if you think about it, you can just take each single element, the set of 1 and the set of 2, and that will work perfect. Because in this set, every element lies in here. Same here, 1 and 2. You also, since it's a regular subset, it's not a proper subset, you can do the set itself, which is 1, 2. But we actually have a 4th subset, which is the empty set. Because if you think of it in definition terms, every element that is in this set does lie here because we essentially have no elements in there. So by default, that works. And that's pretty much a definition, is the empty set's a subset of any set. Sometimes people find that confusing, so the illustration I use is, let's say that the red marker and the green marker are my 2 elements. Say red's 1 and green is 2. Well, if I were to put these markers in a bag and draw them at random, there will be 4 possibilities of what could happen. I could draw the 1, I could draw just the 2, I could draw both of them out of the bag, or I could choose not to do any of them. So it kind of, if you think along those terms, that is all of your possible combinations, including none, which means it's the empty set. So let's do one more of these. And we're going to do the set ABC this time. And what will happen if you think about the last one, if we want to list all the possible subsets of this set, we could do the individual elements, which will be the set of A, the set of B, the set of C. You also could do 2 element subsets, which would consist of AB, AC. I just compare A with both of them, and then you can do B with C. Order is not a factor here, so the set AB is the same as the set BA, so you don't overwrite those, because you could flip the orientation and come up with new sets, but that's basically the same set. So the orientation of the elements that were actually within the set have no bearing. So basically the set BA is the same as the set AB. And then of course you would have, to finish out, you would have ABC and the empty set. And interesting, we're starting to establish a number pattern here. I'm going to write this down. This had 4 answers. This has 8. 1, 2, 3, 4, 5, 6, 7, 8. If you do, I'm not going to actually write these down. I will give you this question, and you might want to do this one on your own and then self-check with my slides. But basically, you're writing every combination down. The idea is, I think you got, is that you're basically looking at every combination. It's just a matter of getting them all down on paper. If you were to do that, I will put the answer up. You would have the empty set, the sets of A, T, and H. You would have the two element sets, MA, MT, MH. And what I did there, I will explain that. I just started with M and compared everything. M to A, M to T, M to H. And then what I did was I took A, which has already been compared with M, so that's out. All I have to do is A with T, A with H. And when you get the T, you compare T to H, and you're done with all the two element sets. And then what I did is just knock a letter out. So knock out the H, gives you MAT. Knock out the A, knock out the M, and knock out the T. I didn't exactly go in order there, but I think you got the gist of what I just did. And then, of course, you have the set itself. That gives you 16 subsets. Note on the next slide. Again, some of these I may skim through just for time constraints. But certainly email me if you have questions about them. But if you had the set C, there's only two subsets. There's the empty set and the set C. So that's kind of a no. But see, that gives you two. So there's a pattern if you do. Maybe I can squeeze it in down here. If we do the set C, we have the empty set and set C. So we have two elements, followed by 4, followed by 8, followed by 16. If we put that in the chart, this is what happens. As you know, one element gives you, in the set gives you two subsets, 2 gives you 4, 3 gives you 8. We just did 4, showed it was 16. It gets to be kind of a little bit tedious after that point, so we'll not go past that, but the number pattern will continue. It will be 32, 64. And if you'll notice, there's a pattern there, starting with no elements. By the way, the empty set has one subset, the empty set. So that's why I wish I had a pointer here, but if the number of elements in the set is 0, then it has one subset, just the empty set, followed by, 1 will have 2, and that pattern just works right out. It's powers of 2. Think back to your binary numbers. We've worked a lot with expanding out the powers of 2. In fact, we used that number pattern before, going 1, 2, 4, 8, 16, 32, 64. So you have seen that from your number system unit. But anyway, 2 to 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, and the pattern just falls right out. As a result, we have this neat little formula. So, the formula to find the number of subsets of a set A with n elements is 2 to the n, as we saw from our chart. There is a number pattern there. And I will do one example of this, and then there may be a couple others built into the PowerPoint that you can work on your own. The nice thing is you can work them and check on the next slide to see if you're doing right. And then again, you can email or contact me if you have any questions. But the question says, how many subsets does a set A have with 6 elements? And the answer would be 2 to the 6th power, which if you multiply that out, that is 64 subsets. There is a high chance that there might be a question on this on the test. And it all is just based on knowing this formula 2 to the n. Write that a little bit bigger. Let me point something out. I think I actually will go to the next example. If you have a large number of elements, say 12, you would compute 2 to the 12th. This is number 6, by the way, in your PowerPoint. And that will be 4,096. So that's a lot of subsets. In fact, I traditionally give one fairly high on the test. And occasionally I have a student that forgot to memorize the rule and they'll try to do it by hand, and they'll realize right away that this is going to be hard to do, because if you write down the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which has 12 elements, well, if you try to physically write all those subsets, you're going to be writing for a while. So just go straight to the formula, which will be 2 to the 12th, and that will be 4,096. So please pay strict attention to this formula, because I can imagine on this second test, you know, if you don't know that, then you're wondering, why did he put such a hard question on there? It's not hard. It's just you've got to remember the formula. So don't forget it. So 2 to the n is 4,096. And that will wrap up the units on subsets, because basically if you can chase elements and tell, given two sets, if they're subsets or not, you should be able to do that. You should be able to, on these preview, I'll just pull it up again, be able to write out the actual subsets on an example that has only a few elements, maybe 2 or 3 or 4, and be able to use this formula I just talked about. So that, really in a nutshell, if you can do those 3 things in the subsets unit, you should be good for the test. So just make sure you work the online homework and work any problems that might be beneficial out of the book. Also, when I refer to online homework, right now, currently this summer, it'll be WebAssign. That will change as different courses go by. So I may reuse these videos, but for right now, we're using WebAssign. If you have any questions then on the subsets unit, please email me. The next section will be on union and intersection.